So in reinforced concrete walls, as I said, this is going to be covered in 3 slide sets, 15, 16, and 17. We're going to start here with general idea on reinforced concrete walls. It's going to be the standard concrete walls that you may see around. We mainly use it for pavement walls, we use it for gravity walls, retaining walls, for also shear walls. So you're going to see lots of applications for it. Sometimes you have this kind of transparent walls, if you like. It's made out of concrete, but not very common. The EGCE code, the 318/2014, recognized walls and just call them structural walls. So the term that you're going to be using here is going to be called structural walls. So in general, let me put this down. You can say this is going to be called here. I'm going to put here a comment. I'm going to say structural walls in the EGCE 318. When it comes to practice, we have 2 types of walls. Some walls are called just gravity walls, and other walls we call reinforced concrete shear walls. So we have gravity and then we have shear walls. This is the 2 names, very common names that we'd like to discuss with any engineer. You call it either a shear wall or it is going to be gravity wall. Gravity walls means walls supporting gravity loads. Gravity loads give you like dead load and life load, any weight of any object, and it's going to be supported by the wall. So it's going to be basically like a column. I'm going to say here similar to columns.
Professor.
Yes.
So gravity walls are the same as like bearing walls? Or?
Yeah, this is correct, but it's going to be concrete.
Okay.
Right? Yeah, it's going to be made out of concrete.
Thank you.
Right. Yeah. So when we say here gravity walls, you understand that just supports gravity loads, dead load and life load. But once you say shear wall, now I know it's going to be used to resist horizontal forces like seismic, earthquake forces, wind forces, and stuff like this. So I'm going to say this is going to be like for seismic and wind forces. Does it mean that shear walls do not support gravity walls? I'm going to say no. These support also gravity loads. So I'm going to say seismic and wind forces mainly. And of course, gravity forces. For gravity loads. So difference between the two, the first type, which is gravity walls, just support gravity loads. The second type support all type of walls. But mainly is going to be seismic forces because this is why you call them shear walls. When you go to the code, you don't see this wording. You don't see gravity walls and shear walls. But they tell you if the wall supports this much shear force coming from seismic or wind, here are the design guidelines. If it just supports gravity loads, here are the design guidelines. So not necessarily that you call them gravity walls and shear walls, just call them structural walls. This is in the code. But in practice and between engineers, we don't use just the term structural walls. We say gravity and shear. This is a standard way of calling walls. Here is a standard wall, just generic one. And you see here, this gives you the wall. This gives you the top of the wall, bottom of the wall. And you not necessarily you're going to have a section like this. You're going to have a box here in the top, like concrete member on the top, concrete member at the bottom. This is not really important. You could just have this piece of wall. I mean, in reality, you don't really need to have this piece and this piece top and bottom. No, it can be just the wall. And this piece here can be embedded in the concrete itself. It can be the same thickness as the wall thick. This wall here, structure wall, exposed to axial forces like gravity loads, dead load and life load. In plane shear, this is gonna be like seismic and wind. Same thing here. And the outer plane is gonna be exposed to same thing, lateral forces, horizontal forces. This is gonna be like seismic and wind. And also it can have some moment. You know, once you have any lateral loads, it means that you're gonna have moment with it. Because if this wall is like a cantilever system and you're gonna be supporting it here at the bottom, you have any lateral forces, it's gonna be creating moment at the bottom of the wall. In the top of all of that, this will also support itself. It supports the self weight of the wall. It is part of what's supporting. Very similar to columns. Columns support, let's say, floor loads, roof loads, and also the column self weight. It has to be part of it. So if you take a wall like this and remove this shear and remove this out of plane shear and remove this moment and remove this moment, I may call it gravity loads. So if the wall supports only the axial force and the self weight, it is going to be a gravity wall. Once exposed to lateral forces and shear, I'm going to call it here shear walls. Okay, good. Any wall, any structural wall, when you design it, you should be able to resist the design forces. Once I see here design forces, it's going to be this part. I'm going to call here design force. So what's the design force? Design force can be an axial force, moment, or shear. Can I call all of that design forces? So why should I call this? I mean, if this is going to be the design force, I'm going to call this going to be the capacity, right? This section is going to be the capacity. Or strength. But here I can call design forces, or I can call it ultimate forces. Also, I can call them factored forces. Any of that works. So you need to have more strength than the demand. Sometimes also we call this demand, right? Demand forces. You need to have more capacity than demand. It can be, again, can be axial force, moment, or shear. Like what you see in the picture. You have axial force, shear, and then you have also moment. This wall needs to be designed to support all of these loads. In walls, we're going to put reinforcement, and the reinforcement is going to be in both directions. It's going to be in the vertical direction and horizontal direction. Let's say, if I look here at this wall, where's the vertical direction? Where is this vertical reinforcement? You can see this rebar here is going to be vertical reinforcement. I'm going to put next to it, I'm going to say vertical. How about horizontal bars? Oh, we're going to run it this way. You put like this, horizontal bars. And here's going to be vertical bars, right? Vertical reinforcement. Just give you the horizontal reinforcement, which is give you this bar. Now, when you put the reinforcing, do you just put one layer in the middle of the wall, or you put two layers? I say, well, it depends. In some cases, I put two layers. In other cases, I'm going to put here 2 layers. I can show you a quick example one actual project. It's good that I am at my computer now. I'll just show you one sheet. Show the reinforcing. This is actually there, all of that, they are all shear walls. And you look at the information provided. It is 8-inch thick concrete or reinforced concrete shear wall. It is true that the code doesn't call it shear wall, call it structural wall, but in my drawings, of course, I'm going to call it shear wall. And you see here the reinforcement, it says number 5 at 16, vertical, each face, which means I'm going to have here 2 layers of reinforcing. And here I see number 4 at 16, horizontal, each face. Okay. I see here some details. So let me open the sheet for you, 142. This means I'm going to be referring here to detail 5 and detail 4, right? In sheet S142. Here is sheet 4 and 5. Here is sheet 4. So what happened? At the end of the wall, I have 4 number 6. It's going to be vertical bars. We call this jam bars, like the boundary element. In the middle, I have here number 5 at 16. This can be the vertical rebar. This is a section here looking at the bottom, looking down, plan view. We call this boundary section or boundary element. As you see here, this can be like the wall rebars. I have 2 layers. Here's the vertical rebars and horizontal rebars. This can be this can be the rebars, right? Because this section looking down. It can be the boundary element. This is actually it's gonna be like the 4 number 6. This is here the 4 number 6s that I'm looking at. Is gonna be right here in ties. I'm gonna put some ties around it. And this gonna be the wall reinforcing, meaning this gonna be the number 5 at 16. Number 5 at 16 is gonna be those vertical rebars. Let me point at it. This gonna be like this rebar. Vertical line. Number 5 at 16. 16 inches gonna be the spacing, meaning the distance from one rebar to the other rebar is gonna be 16 inches. It's gonna be the horizontal rebar. And it says here number 4 at 16. Where do I get that from? I'm gonna say from here. And they have 2 layers. This is why it says here each face. So, okay. If you have 2 layers, it means if I'm designing this to support gravity loads, like a column, I need to take all of this reinforcement, the vertical reinforcement, not the horizontal ones. And usually, if you'd like to design the capacity of this wall, you're going to be taking a piece, is going to be having the wall thickness, and the other dimension is going to be maybe 12 inches. You remember, like in slabs, we used to consider 12-inch strip width. It's going to be the same treatment here. And just take this section here and design it. It's okay. Let me go back to my slides. And let me try to see what does it mean by this vertical reinforcement ratio, rho sub L. L stands for longitudinal. But instead, I'm going to call it here rho V. The code doesn't say rho V. The code just say rho sub L, longitudinal rebars. And it calls for rho T, transverse. I prefer if I call it rho V and H. It's just simpler for me. Because usually someone's going to say, what does it mean by rho L and rho T? But if you just put it as rho V and rho H, it's going to be much simpler. People knows where are the vertical reinforcing, where is the horizontal reinforcing. It's going to be much easier and simpler, in my opinion. So what is this vertical shear ratio? Vertical shear ratio is going to be AS vertical divided by the cross section of the wall. In a case like this, I may just refer to my detail. I'm going to say, okay, let me take here the reinforcing. And the distance is going to be from here to there is going to be 16-inch, the spacing. So the width here of this piece is going to be 16-inch if you like. And try to find out the reinforcement ratio. Now I have 2 rebars, number 5, because the vertical is going to be number 5. Thickness of the wall, of course, is going to be given. And the spacing, I have it. So I should be able to find out this rho sub V. So again, what is rho sub V? Total cross-sectional area of the vertical reinforcement divided by the cross-section area of the wall. How about for this horizontal? How can I figure it out? I'm going to say, you know what? Exactly same section that you have done by looking in plan. Let's give you top view. You can do it, but look in the side. Like, for example, you take a section like this of the wall. And then you figure out how much reinforcing running in the horizontal direction. Divide by this cross-section area. It's going to give you this ratio, reinforcement ratio. Reinforcement ratio is unitless, no units. So let me put this down here. Yes, say here reinforcement ratio. Yes, say unitless. It's going to be for both, right? Doesn't have any units. So great. Is this important to my design? I'm going to say yes, because the code here is going to give you some minimum values that you need to satisfy. The ACI code gives you this table. Is copy and paste from the ACI table. It says table 1161. It says minimum reinforcement for walls with implant shear less than 0.5 PVC, which means very low amount of shear. So when you have low shear, I'm gonna call it here gravity wall, but the code doesn't call it gravity. I'm just gonna call it here gravity in my lecture, in my analysis, my business. So I'm gonna say here low shear. So when the shear is low, you have a special treatment for the wall. But when the shear is gonna be getting higher, look what happened. I don't know if you have it here. No, it's gonna be next slide set. When the shear is gonna be higher than this value, we're gonna have different minimum values. Makes sense. We're gonna have separate treatment. I mean, for each type of walls, whether it's gonna be gravity or shear wall. Detail here, you wanna figure it out. Okay, they give you here minimum longitudinal Rosabel. I have written this V right next to it because I'm confused which one is which. Right? So longitudinal means vertical. So I'm gonna say here vertical. Transverse. So I put this H, I put this V. It is not in the code. I just added to my slide. They say, well, it depends. Do you have cast in place or it's gonna be precast? What is precast? Precast, this is gonna be concrete wall that they cast it in the factory or at the yard. And once it's cured and ready, we can just ship it. We can move it on a truck and move it to your construction site, and then you can install it there. Not very common. This gonna be maybe the common walls. This gonna be this cast in place. Cast in place that you have form work, you have hollow forms, you have the reinforcing, and then you put it at the site. We have two types of bars when we work with bars here. We have this deformed bars, which is a conventional bars. This is the bars we know about. That we know about. About this bars, welded wire reinforcement, I'm gonna say this gonna be very thin reinforcement that maybe you guys have seen it maybe in some you know, like for slab and grade driveway. I'll show you some of these applications. Here we go. It looks like this. It comes welded, like in a mesh. They just put it on the ground. It's not going to be this. It's going to be like this, and just put the concrete on the top of it. So it's going to be like a cheap option. And the cross-section area of this rebar is going to be very thin. It's not really a big thing. This is why it says here, look at this W31, D31. This is going to be very thin rebars, smaller than number 3. It's just cheaper. In many cases that you have a driveway, you don't really want to put an actual reinforcement like number 3 or number 4s. You can use welded wire reinforcement if you want to. And they are available in the market. Home Depot, you go there, you can pick it up. Or maybe like Ringer, you can just buy it from there. It's available. It's simple. Not really tough to find. But mostly in our business here, for our courses, we're going to be working with deforming bars. It's okay. Now I'm narrowing it down, right? I don't need this, I don't need that. It says here, if you have reinforcing number 5 or smaller and bigger than number 5, you have number 6 and bigger. Okay. If the yield difference is going to be equal to 60 KSI or more, or less than 60 KSI. Doesn't happen a lot, this one nowadays, you know. The only available steel is going to be 6 KSI. In the past, we used to have 40, but not anymore. Not available now. And then they give here the minimum reinforcement needed for vertical and horizontal. So you need to decide, are you using number 5 and smaller? It's gonna be here, 60, here's the minimum vertical, minimum horizontal, that's it. If you're gonna go, let's say with more than number 5, right? Like number 6, number 7 rebars, here's the minimum vertical, minimum horizontal. So you need to be able to read this table and just go through it and pick the appropriate minimum steel ratio that you have in here. Okay. Spacing between rebars, that was the other issue, right? So I'm gonna go back here to my slide. I'm gonna say, okay, here's the detail. Spacing between vertical rebars and spacing between horizontal rebars. This could be the issue. Here I'm showing it 16-inch on my design. This is an actual project. So let's see here what it says. It says that the spacing here shall not exceed, which means this is gonna be the maximum spacing. It's gonna be 3 times the wall thickness. So someone's gonna say, is this edge like the wall height, like 10 feet or 20 feet? I'm gonna say no. This edge is gonna be the wall thickness. We're talking about maybe 8 inches, 12 inches, 10 inches. Like in the project I showed you, I made it 8 inch because one story and not very heavy. 8 inch was okay. So if I have an 8-inch wall, the maximum spacing is gonna be either 24 inches, 3 times 8, and 18 inches, gonna be the lesser of the two, the smaller of the two values. So usually it's gonna be 18 inch. In our design, we like to use 16. 16 is a very common number in our design. We'd like to go 12 inch, 16 inch, stuff like that. It's giving multiple of 8 inch spacing. It says here in this section 11723, it says for walls, once you go greater than 10 inch, you should have here 2 layers. Is it necessary that for 8 inch that I need to have 2 layers? I'm gonna say no, but I needed it here in my design. Different issue. But once you go to 10 inch and greater, you need to put 2 layers. It says here greater than 10 inch, but in general, once you go here to 10 inch, you just put 2 layers. About the spacing for horizontal reinforcing is giving the same thing, 3 inch and 18 inches. So spacing horizontal and vertical is almost the same. Example.
Professor?
Yeah.
So if you only had 1 layer, would you just do it right through the center of the wall?
Yes, you put in the middle of the wall, right?
Okay, thank you.
Here's a thick wall. It says here 18 inch thick concrete wall designed to support gravity load only. Okay, gravity load meaning I'm going to be doing this business. It's going to be the minimum reinforcement, right? Did you see here when I was doing the minimum reinforcement, did I check the vertical capacity like an axial load? I'm going to say no, we didn't do any axial capacity yet. This is just the minimum. Like if you remember when we were doing columns, we had this 1% and 8%, correct? Minimum and maximum. But in here it says minimum and this not 1%. This is going to be, if you look at this number here, this means what? 0.12%. It's going to be very small amount of steel that you put in a wall compared to a column. So it says 18 inch, the minimum vertical reinforcement, ACM 615, grade 6C, to be used as minimum. You'd like to put as minimum or as small as possible when it comes to reinforcing. And then it says minimum horizontal is going to be what? And when you look here at this reinforcing pattern or program, you say number 5 at 12, 6 at 8, 7 at 12, 5 at 18. Which one would give you think, the smallest amount of reinforcement? Is it number 5 at 18 or number 5 at 12?
5 at 18.
18 is going to be less. It's going to be the smallest if you like. Next to it is going to be slightly larger. Next to it is going to be number 6 at 8 or number 7 at 12. I don't know. because number 6 and number 7 not the same bar size, but I know that both of these two options, B and C, is going to give you more reinforcing than number 5 and 12. Let me figure out the amount of reinforcement or the reinforcement ratio that I have for each one of these choices. So, okay. First choice, number 5 and 12. What does it mean? I have each face, which means I have 2 bars. So why do I have here 2? Because I have each face. Here's the reason. Yes, okay. 0.31, what is this 0.31? Let's say 0.31 is for A sub B for number 5. When you look at the steel, the reinforcing bar table, you're going to see here number 5 is going to be 0.31 square inches. Then I need to divide this by the spacing. So what is the spacing here? 12 inch. So you can say here's the spacing. I'm working here with 12-inch section, like very similar to slabs. So actually we have done this in slabs, but the difference is you're gonna have here 2, because usually you're gonna have 2 rebars, 2 sides. So we're gonna say 12-inch for the strip width or section width. Okay. Let me repeat it here. I have number 6 at 8 inches, 2 rebars, because I have each face, 0.44 cross-section area for number 6, 12-inch the strip width. So this is going to be the same for all of them. Now divided by the spacing, the 8-inch. Repeat it again for number 7, 2 rebars, 0.6, 12-inch the strip width, and 12-inch is the spacing. Same thing for number 5 at 18. Now, which one's the smallest? You can say this is going to be the smallest. It's going to be the one right above it, 0.62, and then 1.2, and then 1.32. This is going to be my choices in order. Okay, let me see here the minimum needed. In my case here, I have number 5 rebars that I'd like to check, because number 5 is going to be my first option. I didn't want to start with number 6 or number 7. So I'm going to say for number 5, grade 60 for all the rebars, how much is the minimum reinforcement? It says here 0.0012. So okay, let me go here back and look at the table. Deformed bars cast in place, number 5 and less, 6 KSI 0.0012. Yeah, that was the correct choice. Horizontal 0.002. Let me work with this. Okay. Let me find out how much reinforcement do I need per foot. Where is this foot coming from? It's coming from this, the 12-inch section. Okay. Let me see here how much reinforcement I need. I need 0.0012 times 18. What is this 18 inch? I'm going to say this is going to be the wall thickness, right? Called here H, lowercase. Times 12-inch, the strip width, which is the same as this. With that, I need 0.26 square inch per foot. Which foot? Where is the foot coming from? I'm going to say come from here. Come from this one. I need minimum 0.26 square inch per foot. Which option can I go with? I'm going to say this is going to be for number 5, right? So this option should be good. I can just go with this. Because 0.41 is covering the 0.26 square inches. So my choice was okay. I can go with answer D. Let's just say now I'm done with the analysis, right? I'm done with my design. This is good, done. But let's say I decide here to go with number 6 or number 7. What's going to happen? Let me go back here in my table and see what the steel ratio. It says here if number more than number 5 is going to be 0.0015. If I'm going to go with this rebar size. 0.0015 multiplied by the wall thickness multiplied by 12-inch, I need 0.324, and in this case this is going to be like 1.2. It's going to be too much. So actually this option is not good, right? It's just a test. You can say here, not good. I don't really need to test this. Not good. All right. My choice at the end, number 5 at 18-inch, which means answer D. Now I'm done. In this problem here, the question was only about what is the minimum vertical reinforcement ratio, given that no loads was given to me. No one gave me here any loads. All what they give me just ask me how much is the minimum design. That's it. Provide that no loading is given yet. So what I'm trying to satisfy here is going to be one code issue, which is a minimum reinforcement ratio. But if I give you here design loads, you need also to be sure that this reinforcing and the concrete provided and the strength and the whole thing, that's going to be more than the demand, like satisfying this equation. But we didn't do it here in this example because there's no loads given. Any questions? All right, let me do here the horizontal reinforcement. Horizontal, as we said, looking at the table, the first section, it says 0.0012 for the vertical, 0.002 for the horizontal. Let me go back here just to confirm. Here are the two choices. This is going to be vertical and this is going to be horizontal, 0.002. It's okay. Let me take the 0.002 and use it. It's okay. 0.002 times 18-inch, the whole thickness, times 12-inch, the section width. I need here 0.432. If I use here number 5, I look here at this analysis, I'm going to say, you know what? I cannot use this, right? Because I need 0.43, and if you'd like to use option D, it's going to be only 0.41. When you look at all of these options, you're going to say, let me try the second in order. Which one is the second? You can say this one here, the 0.62. It's more than 0.43. This is good. So I can go with this answer. Yeah, look at the final answer, number 5 at 12. It's going to be the good choice. It's going to be less reinforcing. If you don't want to use number 5, guess what? You're going to put maybe double the amount of reinforcing if you decide to go to number 7 at 12. It's going to be just too much reinforcing. Not a good option. So I just stay with number 5 at 12, each face, which means 2 bars at 12 inches on center. Questions before I move to the next example?
Yeah, Professor, I have a question.
Yes, absolutely.
Does that chart above take into account
This
like
one?
is that per no, the chart for section 11.6? Like, is the 0.0012, is that per foot, or is that just in
No,
general?
this is a steer ratio. This is unitless.
Okay, that's a ratio. Okay. Gotcha.
Yeah. So you take this ratio multiplied by the cross-section area of the concrete, you get amount of reinforcement as an inch squared.
Okay, thank
If you
you.
take a strip, no problem. If you take a strip here of 1 foot, like what we're doing, is going to be inch squared per foot. Ready for the second example? All right, second example here. They give me here, they say 8-inch thick reinforced concrete wall. Looks like one of my walls here. 8-inch thick reinforced concrete wall. Designed to support gravity load only. Okay. Dead load 5 kg per linear foot. So for each foot of the wall length in plan view, this when you look in plan view, this is like an elevation, right? So for each foot here, let's say that this give you 1 foot, right? From here to there. About a foot here. For each foot, you have a dead load of 5 kg per linear foot and live load of 3 kg per linear foot. Now I guess I should be able to design the wall for this load, right? You have gravity load axial vertical load, like a column. Concrete strength 2500 psi, grade 60. Select the vertical reinforcing needed for this one. Now I have 2 issues. Issue number 1, I need to satisfy the minimum requirement by code, like according to the table. Issue number 2, provide enough capacity to support this demand on it. Okay, so 2 issues here, not just like this previous example. No, we're going to have here 2 issues. can say first, let me find out the ultimate load, my demand. I have here 5 kPa foot, 3 kPa foot for each foot of the wall. I'm gonna try here the two equations, 1.4 versus 1.2 plus 1.6. Which one controls? I'm gonna say second equation controls. I have 10.8 kPa foot. Great. This is now my demand. Now the wall thickness is only how big? Anyone remembers? It says 8 inch. And then my section is gonna be 8 times 12. Where is the 12 coming from? You can say coming from here. Let me put the other slide. Put it here. I'm taking here a section of this one. This length is 12 inches, and this thickness here is 8 inches. I'm going to be designing this section. Give me a second, please. So taking this section of the wall, I'm going to say this dimension here is going to be 8 inches from here to there, like the height of the section. And this length is going to be the standard wall strip. I'm going to say 12 inches. Now I need to design this. 8 by 12. Okay. 8 by 12, 96 square inches. AS minimum. Now I have for the vertical 0.0012. I'm using here number 5. It's going to be 0.115 square inches. I need to decide on the spacing. So I'm thinking I can go to the spacing of 3 times h, the wall thickness. See, this is going to be here the wall thickness. Three times 8 is going to be 24 versus 18 inch. I'm going to go with 24 with 18 inch, the smallest of the two. Can be using number 5 at 18. This is going to be my choice. Guess what? Number 5 at 18 is going to get me 0.206 square inch per foot. How do I know that? 0.31 A sub B, 12 inch the strip width, 18 inches give you the spacing. Now, provided it's going to be 0.206 square inch per foot. Needed 0.115. My choice is good for the minimum. So comparing this to that. So I'd like to use this. Now, do I think that I'm done here with my analysis, my design? I'm going to say no. How about the axial load capacity? I need to check it out. I just picked the smallest amount of reinforcement. That's what I've done. Now I need to be sure that it has enough axial load capacity to support the gravity loads, which is a 10.8 kPa foot. So what I would do here, I'm going to be taking this amount of reinforcement and this A sub G and try to find out the capacity as if this is a column. I say, okay, number 5 at 18, here's AS. Just use my standard equation for type columns. Say 0.8 times the phi factor, 0.85 A sub G minus AST for the steel. And here we go. I said here 0.8 times the 0.65, the phi factor, right? 0.85, 2.5 KSI, concrete strength. A sub G 96 square inches minus 0.206. A sub ST plus 60 KSI. This is going to be F sub Y times AST. How many kips do I have here per foot? You say 112. Wow. Your demand is only 10. So this wall is strong enough. This is a standard way of designing a gravity wall. And just, you know, it is very standard that we start with the minimum reinforcement in walls. So we try to just cover this minimum. And then after that, we find out the capacity of this wall for axial load, for flexure, and for shear and the whole thing, and then compare it with the demand. But usually we'd like to start with the minimum because we know that in walls, we have lots of concrete. It's going to be very strong compared to the demand. Look at the demand here and the capacity, like 10 times. Sometimes, I mean, it's going to be at least maybe 2 times when it comes to axial load capacity. Because concrete wall has big cross-section area. Okay. Any questions? You're good? Project on a wall design of 14 inch thick typical wall on grid line 3 between grid lines B and C. So grid line 3 between B and C. Which wall is this? We can say this is going to be your wall that you need to work on. Right? Then it says here total axial load on the wall is 9 kP per linear foot. Now, do you need to do tributary width? No. I give you the load already, 9 kP per foot. Live load, 5 kP per foot. Consider the wall length as 29 feet. So don't try to measure from here, just take 29 feet. It is given to you to be 29 feet, please use it as 29 feet. Rebar size is given number 5. Determine the axial load demand, service and factor on the concrete wall. Service, just add in. Factor, you need to try both options. 1.4 times dead versus 1.2 dead plus 1.6 live. Don't just do the 1.2 dead and 1.6 live. You need to do both of them. You need to try both of them. Be sure that you do that. Otherwise, you're going to be maybe losing some points. Now, maximum vertical, horizontal reinforcement needed. You say, okay, horizontal, you're going to be using the minimum. Vertical, also use the minimum first. And then once you do the minimum, this can be the minimum, right, based on the code equation. And then after that, determine the needed reinforcing based on the axial load demand. Now, this is when it comes to this last exercise that we have done. So first to find out the minimum, and then you check the capacity. If the minimum is good, you're fine, you're done with this exercise. So this submittal should be very simple. And this is going to be your last submittal for the course. I have also a homework for you, which is going to be due the same day. It gives you here concrete bridge, reinforcement 615, grade 60, concrete strength 4,000. Consider the effect of the compression reinforcement. So when you do analysis, be sure that you consider the effect of this compression reinforcement. You have here 2 problems. When you have passive moment, what does it mean by passive moment? Can someone help me with this? What is a passive moment? The passive moment, would this reinforcing be in tension or compression? What's the passive moment? Is this going to be in tension or compression?
Tension.
Tension. The passive moment is going to be in tension. How about the negative moment? Which one's going to be in tension? The top or the bottom? We say the top now is going to be in tension, right? And the bottom is going to be in compression. So we're going to say, how about this web? I have here 3 webs. What should I do about it? So you know what? Just assume that all of the 3 webs is going to be just like one web, very similar to what you have done before. Just add it together. It's going to be like this. With a width of how much? 12 inches. Just one piece. It is gonna be your lucky day, right? It's like 12-inch. Just forget about this. It is gonna be your lucky day when you find out a compression block depth, and then all of a sudden you find it to be happening here, right? Within the flange thickness. Or if you have negative moment, it happens within this 4 inches. You're gonna be very lucky because it is not really a T section. It's gonna be a rectangular section with compression reinforcement. Question is this critical? This problem here, is it critical to solve this? I'm guessing yes. It is important. If you want to get ready for your final, you need to know how to do this. So consider it to be important and consider understanding it, not just solving it. Any questions on the homework and the submittal? Submittal is going to be so easy. You can just follow this example. You have a very nice example. You can finish it quick. Questions before I move forward? All right. I let you go earlier a little bit today, so you have fun. You guys ask me if you have any questions. Otherwise, I'll see you next time.
Thank you, Professor. Have a
Please
good
sign
day.
out. Yeah, please type your name and your way out, please. Thank you.